Amir Yehudayev. Okay, so I'm going to start this talk with an open question, and we're going to build a model from it. So the setting is as follows. We have two agents, Alice and Bob. Each of them get to observe their own sample. In this case, we'll say that Alice saw the blue points and Bob saw the red points. And what Alice and Bob want to decide is whether there's a hyperplane that separates the two sets. Okay? And they don't know each other's set. So what can they do? They are allowed to transmit samples. Okay? So Bob can give Alice his sample, and then Alice can send samples to Bob, and so on. And the question is, how many examples do they need to transmit? Okay? So this is we don't know the tight bounds for this, so I'll show you the bounds that we get in this work. So we have an upper bound of d cubed log n, which I'll try to illustrate in this talk. And we also have some lower bound that shows that you need, so d is a kind of a trivial lower bound, but we also show that you need log n examples, okay? But what is the correct bound? That is something that we don't know, and we will be happy if anyone here would want to improve on these bounds. Okay, so I think the model kind of is natural after this question. Instead of hyperplanes, half spaces, we can think of any hypothesis class. Alice and Bob gets to observe their sample. Maybe it's not even blue labels for Alice and red labels for Bob. Maybe they each get to see both labels. But overall, they have their hypothesis class, and we want to decide or learn whether there is a good hypothesis in the class that separates the sample. And you can think of this setting in the realizable proper case, the irrealizable improper, agnostic proper, agnostic improper, and so on. As before, they can communicate with samples. They can transmit samples to each other. And the main question is sample complexity. You want to know what is the sample complexity of the hypothesis class. How many examples I need to send if I want to learn the class. If you are familiar with sample compression schemes, then this might be familiar. So sample compression schemes were introduced by Littlestone and Wormuth. And it's a very similar setting, only the difference is that in sample compression, only one part gets to observe the sample. So for example, here, Manfred gets to see the sample, and he needs to transmit to Littlestone a sample that will help him learn what is a true classifier. So for half spaces, for example, it is known that you can send the support vectors. So he transmits those samples, and now Littlestone know how to separate the two samples. More generally, it is known that you can the number of the upper bound of the sample that you need to transmit is currently it's exponential. We know an exponential bound in the VC dimension. It is believed that the true bound is linear. So you roughly need to transmit fixed number of points, size of the VC dimension. Okay, so it is interesting to compare the two settings and see how our results relate to sample compression. So I'm not going to go over all this table and all these results, but I'll just highlight the main result that I find interesting. So for example, if you look at the proper case, what's the sample complexity of proper learning? So in sample compression, we don't know much. We don't know what is anything about proper sample compression, but here we can actually analyze and show, give characterization of classes that are learnable in the proper model. Another thing that is interesting is that if there is the sample compression for this bound is fixed in the sample size, in our model, you get a lower bound of log n. So for a long time, it was not known if you have a fixed size sample compression, and the best bound was logarithmic in the sample size. And in this model, it's also necessary. You cannot do better. Okay, so what I want to do with the rest of the talk is basically to go over the problem of the convex set disjointness, which can be thought as learning properly the class of half spaces, and give you some intuition of the protocol and how we get the d cube. So we're going to show it in the plane. So the main idea is basically to use the boosting algorithm. And it works like this. So at each iteration, what Alice and Bob are going to do is they're going to share a small set which approximates their sample. That means that if you find a good hypothesis on that class, it has a fixed error. So they are going to transmit that sample. And then once they observe this sample, they are going to use it to learn a weak learner, because they can learn a weak learner which is both weak on Alice's sample and on Bob's sample. And then the standard result of boosting tells us that after log n steps, they're going to hold a set of t log n weak learners that their majority is always correct on the sample. But it's also, you can also kind of prove that if they're going to run the algorithm a little bit more, then it's not going to be the majority that is correct, but 7/8 of the hypotheses are going to be correct. And they're going to run the algorithm until that happens. And what I claim is that if the sample is non-realizable, they won't be able to do that. So if they are able to do that, that proves to them that the samples are realizable. So why can't they get a majority of 7/8? So it follows from Kara-Theodori theorem. And the problem is that in any non-realizable sample, you can always find 6 points on which the sample is already non-realizable, because the convex halves intersect. So you have a point that is, can be represented by 3 points from the blue and 3 points from the red. So these 6 points are non-realizable. And then by pigeonhole principle, you get that you cannot have that 7/8 of the hyperplanes are correct on every point. Okay? So, and this result, so, and in this algorithm, you might think that you can generalize to general hypothesis class. The only part where we used something about the special structure of hyperplanes when we used Kara-Theodori theorem. So we can replace Kara-Theodori theorem with the assumption that we need, which is that every non-realizable sample contains some set of size k where the points are not realizable. And so this is a new notion that we defined, the coVC dimension, and it turns out to be necessary. Okay, and to see that it is not necessary, what you can do is you look at singletons. That is a case where the coVC dimension is infinite, and then using lower bounds from communication complexity, you can prove that because they are unable to decide if the set are disjoint or not, if they could learn this class, basically what it means is that they can decide if together the sample is, they have the whole sample labeled as red. In that case, the sample is not realizable. So kind of interesting is we use communication complexity to achieve the lower bound, while we had to use boosting for the upper bounds. Okay, so this is a very short introduction of the results. There are quite a lot of other results in the paper. So like I mentioned, we have a log n lower bound, which is quite involved, and I don't have the time to go into. Okay, so that's it. Okay, so I didn't have the time. So what you can define is similar to defining a hypothesis class where you can learn them. You can define a hypothesis class where you have a short proof that the problem is realizable. We can we can characterize those, and you can define the classes where there is a short proof that the classes are not realizable, and we have a result that says that P equals NP co-NP. It's similar to communication complexity. Basically, whenever you can do the both, then you can solve the problem.